Thank you for coming. Have you enjoyed your lunch? Because we're going to talk about food. Yesterday, Alex, I, and the rest of our friends, we wanted to meet for a lunch. Alex suggested going to Daily Chew at noon because it has vegan options, and Sophie decided maybe it's better to go to BZB at 1 p.m., and I suggested Jamrock. It was not trivial. First, we had conflicting opinions, and second, we had communications issues. We tried calling each other multiple times, but first Alex was in a meeting. Then I decided to take a nap to shake off jet lag, and you can guess it. At the end, we couldn't agree when to meet, and we didn't meet at all. Agreeing on something is hard, especially when communication is not perfect. If only we could have agreed ahead of time how to resolve such situations. If only we had an algorithm on how to achieve consensus.
Well, at least we could agree to be here on the stage at 3 p.m. today. Otherwise, we wouldn't have this talk. Hello, everybody. My name is Alex. I'm Ukrainian, and I'm software engineer at Netflix.
My name is Mykyta. I also happen to be a Ukrainian who works at Netflix, and today we have a remote speaker.
Hi, my name is Vadym. I'm a full-stack engineer at a company called Integration App. Also, I'm a colonel in the Ukraine Army. So for obvious reasons, I will be joining you remotely. Thanks for having me. We are going to discuss today consensus algorithms. A disclaimer, we will use simple language, so even busy army people like myself can understand it. Well, relatively simple language, you don't need to have a PhD or deep knowledge of formal methods, but a general knowledge of distributed systems will not hurt. One of the most common examples of consensus-finding problems is having a group of friends or co-workers to agree on the time or place to meet. It can be a business meeting in person or video call, or it can be a school reunion. I take a liberty to assume that a lot of people here try to organize something along those lines, so you know how hard it can be.
We definitely do, because in fact we face similar problem when we worked on this talk. Group of people who work on this talk, we decided we would meet around once a week. It was Mykyta, Vadym, Sophie, Lloyd, and myself. But we live in different locations, we have different commitments. Some of us can take a day off. Some might not have reliable internet connection. Yet we had to schedule our meetings week after week after week, finding consensus despite imperfect conditions. And this is the simplified example we are going to review today. We have multiple team members, and our team will be trying to agree on a day to meet. Our group will be a cluster, and people will be nodes. We will also have a generative AI assistant who will be suggesting what day we should meet. After we agree on a day, other people should be able to find out what is a day. For example, if my son wants to know if I can make his ice hockey game Tuesday night, there should be a way for him to ask me or other people in the group. I don't want to make scheduling commitments I can't keep. We're distributed, we live in different locations. Some of us are even virtual. To agree on a single value, we need some kind of a consensus algorithm, a distributed consensus algorithm.
Can we just use good old two-phase commit?
We could, and in fact, when a group of people is trying to agree on something, oftentimes we just use a variation of two-phase commit without even knowing it. Does everybody know what two-phase commit is? Okay, let's do a quick recap here. In a two-phase commit, when a value is written by a client, an AI bot in our example, one of the nodes will be acting as a transaction coordinator. Let's say Vadym will be a coordinator because he has the highest military rank, for example. A bot tells Vadym that let's try to schedule meeting on Tuesday. Vadym writes this value to his write-ahead logs and sends this value to everybody. He sends a prepare request first. He's basically asking, would you all agree if we meet on Tuesday? When Alex as a participant receives this request, Alex writes this value down in his write-ahead log in his notebook, locking this value, making sure that Alex will not promise anybody else to meet on Tuesday night. And then Alex tells Vadym, yes, I can meet on Tuesday, I promise, but please confirm and please get back to me when you hear from everybody else. In the meantime, I will not promise anybody to meet on Tuesday night. When Vadym receives those promises from everybody in the group, and this is important, from everyone in the group, then Vadym commits this value. Vadym sends everybody commit message for this transaction, and when Alex as a participant receives this commit message, he makes this value official in his notebook, and now the value is official. As simple as that. This approach is simple, but it has multiple downsides. First of all, it requires promises and acknowledgements from everybody in the group. It might be easy to agree on something when you have 3 people in your group, but when you have 20 or 30 or 100 people, it might not be trivial. If Vadym is proposing to meet on Tuesday, everybody agrees, but Mykyta doesn't, because why?
Because I have a scheduling conflict. I have an immigration appointment on this day. I cannot reschedule it. I waited for it for years.
That's a true story. Then the transaction is aborted, and we need to renegotiate. We need to start from scratch. Also, the coordinator waits from everybody in the group to reply, which means the latency of this commit is the latency of the slowest node in our group. And if someone is slow to respond, Vadym will wait, and everybody else will wait, holding this locked value in the write-ahead logs, not confirmed, not aborted value. And if Alex's son is calling and asking, hey, Dad, can we go on a hockey game on Tuesday night? Alex can tell him, I don't really know, I already promised Vadym we will meet on Tuesday, but he hasn't confirmed yet, so I'm kind of blocked. So one node can block the entire cluster. And it might not be our biggest problem, because if Vadym becomes unavailable, it's even worse. Vadym is in Ukraine, and if he loses his satellite internet connection, what happens then? All of us are blocked. We can't accept new values, we can't commit, we can't roll back. We don't talk to each other, we only talk to coordinator in the two-phase commit. And what if your cluster has dozens or hundreds or thousands of machines? All of them will be blocked.
Yes, but can we do better?
Apparently we can. To see how we can do it, we will cover the 2 most common distributed consensus algorithms, Paxos and Raft, and review how they deal with those problems. In our example, consensus will mean we agree on a single value, a day when we meet next time. And we will use different methods to reach the consensus. But when we are discussing these methods, we should keep in mind 3 properties. First is fault tolerance. When one of us is unavailable or slow or decides to go to sleep, the consensus should still be reachable. Second is safety, which means that at any given moment in time, we can only agree on one single value. And when this value is agreed on, it can be rolled back. We can agree on a new value if we want, but it will be a new iteration of consensus negotiation. Safety means that only one value is chosen. This means that we cannot have conflicting values. And the third property is liveness. This means that eventually we will reach a consensus. This can take multiple iterations, but as good friends, we will agree.
So let's go back to two-phase commit for a second. Does it satisfy all 3 properties? What do you think? No, it does not. And which properties it does not satisfy? Well, it's fault tolerance and liveness. Let's see if Paxos and Raft will do better. Paxos is a very popular algorithm. It's used in many systems that we all know and use, like DynamoDB or Cassandra. It's also believed to be a difficult protocol to understand. Let's see if it's true. Paxos was introduced by Leslie Lampard back in the 80s and by Computer Science Standard. It's ancient protocol, and the example that Lampard used in his paper was a fictional legislative consensus used on the Paxos island in Greece, so it's ancient Greek indeed. Paxos has multiple variations, but for the sake of time, we are going to focus on basic Paxos. And Paxos is voting based, so all of us will vote, and this way we're going to elect a new value. How do we vote? By casting a ballot. Each of us will have a ballot with unique ballot number. Each of us is going to keep track of the ballot numbers, and everybody is going to start with ballot number 1. Ballot numbers must be unique, and we can compare a pair of ballot numbers and names, and we can compare names alphabetically. If our names are unique, ballots will be comparable. Ballot number 1 from Alex is smaller than ballot number 1 from Mykyta, which is smaller than ballot number 1 from Sophie. And Paxos is also a multi-phase algorithm. In phase 1, called prepare, our client, the AI bot, sends one of us a new value. It tells Vadym, let's try to meet on Friday. And Vadym becomes a proposer, and he tries to write this value to the rest of the cluster, and all other nodes, Mykyta, Alex, Sophie, and Lloyd, are now acceptors. Client, proposer, and acceptors are 3 roles defined by Paxos. There are more roles, we're going to discuss them later. But now, proposer Vadym has a value in mind, but he doesn't send it yet. First, he wants to ensure that everybody will vote for his value. He sends a next ballot message to the acceptors. In this message, he says, my next ballot number is number 1 from Vadym. When Sophie receives this ballot number, she's checking what was the highest ballot number that she voted for. And she didn't vote for any, so she accepts ballot number 1 from Vadym and replies with last vote of null. She didn't vote for anything. This way she promises she will vote for ballot number 1 from Vadym, and this promise is not for a value, it's not for a proposer ID, it's for the ballot number. This is important here. And when Vadym receives last votes from the majority of the acceptors, Vadym can start the voting itself, and he can send the Friday value, but unlike two-phase commit, Vadym doesn't wait for all the acceptors. The simple majority is enough, 3 out of 5 will do. And when Vadym receives the majority, he now can send a begin ballot message, which contains a ballot number and the value itself. So it goes like, begin ballot, ballot number 1 from Vadym, and the value is Friday. And when Sophie receives begin ballot, she checks if she promised to vote for this ballot number, not for the value, but for the ballot number itself. And if she did, in our simple case she did, she casts her ballot, she writes down the value as the last voted value, and she responds with a voted message in which she sends the ballot number she voted for and her name. And when Vadym receives this voted message from the majority of acceptors, he writes this value in his notebook, and he sends success message with the value of Friday to all the acceptors, and when they receive this success message, they all write this value down. We have reached a consensus here.
This is the basic Paxos protocol, not so hard, right? To make it all work, every participant, every node in the cluster should track the following values: the number of the last ballot they tried to initiate, the largest ballot number they promised to vote for, the last value they voted for, and of course the current value we all agreed on, which is Friday. But that was happy pass, no issues. Let's try some failure scenarios. Let's say we want to agree on a new value for the following week. An AI bot tells Vadym we should meet on Monday. At the same time, an AI system tells Lloyd that we should meet on Saturday. You see, AI is trying to confuse those humans already. Both Vadym and Lloyd are proposers now at the same time. Vadym sends next ballot number 2 from Vadym, Lloyd sends next ballot number 2 from Lloyd to all the nodes in the cluster. Alex and Sophie receive next ballot number 2 from Vadym and promised to vote, last vote. Mykyta receives next ballot number 2 from Lloyd and promises to vote for Lloyd's ballot. Vadym has a majority now, himself, Sophie, and Alex, and sends begin ballot with ballot number 2 from Vadym and the value, which is Monday. Alex and Sophie see that in fact, they promised to vote for ballot number 2 from Vadym, so they reply voted. But Vadym loses his satellite internet connection once again, and he cannot confirm. Proposer Vadym is not in the cluster.
Remember, this exact failure scenario blocked us forever in two-phase commit.
It did. Let's see what happens in Paxos. In Paxos, we still have Lloyd, who is sending his next ballot messages. And now this message reaches Alex. Alex cannot accept it because Alex promised to vote for ballot number 2 from Vadym, which is larger than ballot number 2 from Lloyd. Lloyd doesn't have quorum, he cannot proceed. At the same time, Lloyd doesn't know about Vadym's proposal because Vadym's message never reached him. So Lloyd increments the ballot number and sends next ballot number 3 from Lloyd. Mykyta receives this message and promises to vote. Alex receives next ballot number 3 from Lloyd, and now the ballot number is larger than the one he promised to vote. So 3 is greater than 2. Now Alex must agree to vote. Also, Alex remembers that he voted for value Monday from Vadym. This value was not confirmed, but he still voted for it. So he sends this information back in the response. Alex promises to vote for Lloyd ballot number 3, but in the response, in the last voted message, he sends back all the information he received from Vadym. Lloyd now has a majority, quorum, himself, Mykyta, and Alex, but he has another information. He now knows that some members of the cluster, like Alex, already voted for value Monday. So what Lloyd does, Lloyd should abandon his value and use this value instead. Monday will be new proposed value now.
Please note that in Paxos, choosing a proposer to vote for and choosing the actual ballot to vote for, the actual value, are two separate steps. And that provides fault tolerance because we don't become blocked if something happens with our proposers, unlike in two-phase commit.
That's right. And the cluster will even try to complete what Vadym started, committing the Monday value. Lloyd sends begin ballot with value Monday to Alex and Mykyta, and now California storm happens. Alex loses power, experiences internet outage. Lloyd doesn't hear back from Alex. Mykyta himself replied voted, but Lloyd cannot record this value. He cannot confirm. He doesn't have a majority. But we still have Sophie in the cluster. Sophie was not part of the initial consensus, so Lloyd needs to renegotiate consensus now. He increments ballot number once again, sends next ballot number 4 from Lloyd to Mykyta and Sophie. Everyone who still remains in the cluster agree. Lloyd now has quorum once again, and he can send begin ballot number 4 from Lloyd with the value of Monday. Sophie and Mykyta receive this value, and they confirm the value is agreed now. We can keep removing and adding back acceptors and proposers, but you might get the idea already, how Paxos tolerate node failures. Alex and Vadym, they are not in the cluster anymore, but the protocol is not blocked. And even more, the confirmed value is Monday. And remember, this value was originally not proposed by Lloyd's assistant. Monday was proposed by Vadym, who is not in the cluster. Then it was sent to Alex, who is not in the cluster. And even though those two are not in the cluster, this is the value that we reached consensus on.
But how do Vadym and Alex know this value when they come back? Is there a procedure to learn it?
Well, in the pure Paxos protocol, in the basic Paxos, they don't have to know until the next time one of the nodes tries to negotiate new value.
But what if Alex's son or Vadym's commanding officers wants to know when the group is meeting? How could they ask Alex or Vadym if Vadym and Alex doesn't know the value themselves?
Well, in the pure Paxos protocol, external observers like Alex's son Igor or General Valery, they don't ask Alex or Vadym. They become learners. And learner is yet another role in the Paxos protocol. Learners are passively observing the cluster. They don't propose new values. They don't vote for the values. They don't vote for the ballot. They're just notified about the outcome, about the result. When the value is agreed, acceptors or proposers will also notify learners. In practice, many Paxos implementations decide to merge those roles. So in practice, oftentimes, acceptors will also be learners. If that was the case, if acceptors were learners, and Vadym was not only acceptor but also a learner, when he is back in the cluster, he would learn this value. But merging those roles is beyond the basic Paxos protocol.
So we have 4 potential roles in Paxos, right?
There are 5. But before we talk about the last role, let's recall the properties of the protocol. Vadym, what do we know about them?
Okay, something happened with the slide?
Something happened with Vadym.
Okay, like we don't have the connection.
Well, that's fine. Let me...
So let's try.
Well, first it's fault tolerance.
We do know.
We saw how the protocol tolerates network failures or slow nodes. Some major traits that make Paxos fault tolerance are: it's a quorum-based protocol, the majority is enough for moving forward. So if some nodes are slow or failing, the protocol is not blocked. It's based on the ballot numbers. And proposer is not selfish. It doesn't try to convince the acceptor to accept the initial value. If it learns that an acceptor has another value, the proposer is willing to propose it instead. How about safety? No two distinct learners can learn different values. There can be multiple decided values. Again, because it's majority-based protocol and learners are notified at the very end. How about liveness? With liveness, it's not so simple.
That is correct. It's not that simple. What if Mykyta wants to cast a ballot in the future? He sends the next ballot message to get the people vote for him. He sends next ballot number 10 from Mykyta, and Alex, Vadym, and Lloyd, they promise to vote for this message. Now Mykyta has a quorum. Now Sophie decides she wants to become a proposer as well, and she sends next ballot number 10 from Sophie. Alex, Lloyd, and Vadym accept her ballot number because number 10 from Sophie is larger than number 10 from Mykyta. Now, Sophie has a quorum, but these things happen simultaneously. So Mykyta still thinks he has the majority, and he sends begin ballot number 10 from Mykyta with the value of Thursday because it was promised for him. Other people promised to vote for him. And now Alex, Vadym, and Lloyd cannot accept his value because they promised to vote instead for ballot number 10 from Sophie. So what Mykyta does, he increments his ballot number and he resends next ballot number 11 from Mykyta, and Alex, Lloyd, and Vadym, they promise to vote for ballot number 11 from Mykyta, and Mykyta has majority once again. But Sophie still thinks she has a quorum and she should begin ballot number 10 from Sophie with a value of Friday. But Alex, Lloyd, and Vadym cannot accept this value because they promised to vote for Mykyta. No, Sophie increments her ballot number and she resends next ballot number 11 from Sophie, and the protocol is not moving forward. This is a live lock, in fact.
This condition is called feature Lynch-Patterson impossibility result, or FLP result. And there is a paper about this condition. The paper claims that in consensus algorithms, you can only have two of safety, liveness, and fault tolerance. There is a number of workarounds to minimize this condition. For example, you can introduce random delay between proposed values. This delay would reduce the chances of live lock, but in theory, impossibility of a live lock cannot be ruled out.
But in Ukraine, we learned that nothing is impossible. Also, we know the importance of leadership. Can we have a leader to decide?
Yes, and in fact, leader is the fifth role in Paxos. One of the nodes can be elected as a leader. Leader is a distinguished proposer, and only leader can propose values. The leader himself can be elected using Paxos or a different algorithm, but this version of Paxos is beyond the basic Paxos protocol. As you might get already, Paxos has multiple variations and implementations, and we will not be able to cover all of them today. Instead, let's take a look at how Paxos is used in real-world systems. Let's see how this algorithm is applied and why it's important to understand how it works, and how you can apply this knowledge to the systems that you build and own.
And one of the most popular databases that uses Paxos is Cassandra. It's not the only tool that uses Paxos under the hood, and those tools are not limited to the databases like Google Spanner or DynamoDB. In fact, Google Chabi uses Paxos, and it's a distributed lock and coordination system. Yet the Cassandra is probably the most well-known example. I guess some of you use Cassandra in production. Who does? Okay, I see some hands. Great. And you may know that Cassandra uses its own version of Paxos to support its lightweight transactions. What are those lightweight transactions? Why do we need them? Why are they important? Well, in NoSQL world, people are used to eventual consistency. However, there are cases where eventual consistency just doesn't work. Sometimes you need to maintain a strict order of reads and writes, and you need to make sure different people don't step on each other's toes. And what does it mean for our case? When we're trying to set up a meeting, when we want to book a room for this meeting, we must make sure that if we book a room, if we make a write operation, that this booking is going to stay there and be visible to everybody else. So all reads that happen after our write should be able to access the booking data, the data that we just updated. This condition is called linearizable consistency.
But how does Cassandra ensure that order? How does it even know we want to use transactions? There is no begin transaction index or anything like that in Cassandra, right?
Well, first of all, there are syntaxes differences. Lightweight transaction system syntax is different from regular operations. When you use regular operations in Cassandra, you may have regular inserts and updates and deletes, but lightweight transactions are compare and set operations that look like insert if not exists or delete if exists, and then update if some condition is met, and if the condition is not met, then the operation fails. If we have two competing bookings that are coming from two competing virtual assistants trying to book the same room, that we are going to have to insert if not exist operation. And the first one is guaranteed to succeed because we have no booking, and the second one is guaranteed to fail because we are trying to insert the record that exists already and the condition should not be met.
How does Cassandra and Paxos fit in this picture? Well, contrary to traditional relational database, Cassandra doesn't have pessimistic lock on the record to prevent concurrent writes. Instead, it's using compare and set operation. And to use compare and set operation, it relies on improved Paxos protocol. Why it's improved? Because it requires read and get results step to check if a condition is met before the value is proposed. Also, this step reads the actual data, not just the ballot number itself.
So if we go back to our meeting analogy, if we see how this compare and set approach works, we are going to see the following picture. The bot calls Alex and the rest of the cluster is doing the regular Paxos song and dance, start with prepare and promise. We already covered what happens during the step. So the next step, the read step, is going to look like this. Alex should ask everybody, do we have a meeting this coming week? Nope, no meeting. The calendar is clear. There is no record. Response everybody. That's the actual read. Then we can just proceed with the rest of Paxos steps. And when a second assistant calls Vadym, we should go through the same motions again. Vadym does the prepare and promise steps, and then he asks everybody if we have anything scheduled and what is scheduled if there is a conflict. And guess what? We do have a conflict. If we have a record that is committed or proposed or promised, the condition is not met. Sorry, Vadym, we gotta fail this request. Abort it right away. Tell the assistant that this booking cannot be made.
As a consolation, though, please note that Vadym does ask about the scheduling data, so the data can be taken and used for error handling. Like, oh, we have a meeting next Monday, maybe we can choose another week and retry. There are more race conditions and failure scenarios in lightweight transactions, but all of them fall into standard Paxos operation procedures that we already covered. So we are not going to spend time reviewing them again and again. Let's wrap it instead with one final look at Cassandra's limitation.
One most interesting limitation is that you should not mix normal operations with lightweight transactions. If you use lightweight transactions, you should use it for all your operations. For example, this series of statements on the left may fail. This one is guaranteed on succeed. Why? Because Paxos requires ordering the proposal, and Cassandra is using a special time-stepping mechanism for lightweight transactions, which is different from regular writes. So you need to make sure you use it properly to achieve the strict ordering.
Wait, it looks like those Paxos round trips, they don't come for free.
That's absolutely true. The whole idea of using Paxos is we are going to have a performance penalty instead of making one write and then just propagating it to the rest of clusters eventually. We're going to have 4 Paxos interactions, and it doesn't make sense to use lightweight transactions everywhere. You need to check if we actually need strict ordering here. For example, if you're booking a room for an important meeting, you really want to prevent double booking, and this penalty may be worth it.
So sounds like lightweight transactions are not so lightweight after all.
They're still so much better than two-phase commit. Yes, 4 round trips are kind of slow, but it's still better than getting stuck forever.
Is everybody with us so far? Does it look too simple? Maybe
No.
No? If it's too much, don't worry. Paxos is complex. It's believed to be complex. So maybe we should choose another protocol for distributed consensus, another algorithm. And speaking of another algorithm, we asked the generative AI service to generate us an image. And here's what we've got. Any idea what the prompt was?
Yes.
And? Yeah, the prompt was Raft and Paxos. And I guess the Paxos is this island in the back, and Raft is probably this beautiful engineering project from wooden sticks.
And duct tape.
I'm not sure I see any duct tape.
I'm pretty sure some duct tape is involved there.
But let's see if Raft is any simpler than Paxos, because when Raft was created, its design goal was to develop the simplest, most understandable consensus algorithm. And how do we, software engineers and designers, reduce complexity? Well, the same way we eat a huge meal, piece by piece. So what Raft does, Raft decomposes the consensus problem into two distinct sub-problems. First is leader election, and another is log replication. Raft is based on the 3 states every node can be in. So only 3 states, 3 roles. And 2 messages that nodes can send each other. That's it. 3 states, 2 nodes. No, 2 messages, 2 RPCs. It's a leader-based protocol. In normal circumstances, one of the nodes in the cluster will be a leader, and everybody else is a follower. A leader accepts requests from our generative AI assistant and replicates the state to the followers. Followers in Raft are totally passive. They just do what leader tells them to do. Leaders in Raft is not being re-elected until they die or become unavailable. So there is no midterm elections or any procedures like that. You elect your leader once, and then you don't complain they're a bad leader. You stick with them forever until they die. This would be suboptimal political system. We might know some examples, but let's see how it works for distributed consensus. Just like Paxos, Raft is based on the idea of generational clocks or monotonically increasing numbers. In Raft, they're called terms. Every node in the cluster knows who is the leader and what their term is. But when we start, there's no leader in the cluster. So every node starts as a follower. We need a leader for this cluster. And one of the nodes, let's say Sophie, discovered that, oh, there is no leader. So Sophie wants to become a leader. But before she can be a leader, she becomes a candidate. She self-promotes herself into be a candidate. She increments ballot number or term number. Term number is 2 now. And sends everybody a message. Request what message? Remember, we told you that Raft has 2 messages. So request what is one of those messages. At the same time, Mykyta realizes that, oh, there is no leader in the cluster and becomes a candidate. See, he increments term and sends everybody request what with term 2. Sophie and Mykyta are both candidates now. Vadym got a call from his senior officer and left the cluster. So we have only 4 nodes in the cluster right now. Alex receives request what message with term number 2 from Sophie, and he will agree to what with her. In Raft, when a follower receives request what message, this follower votes unless it has already seen a request with the same or higher term. Alex only saw term number 1, so he votes for request what term number 2 from Sophie and stores this term that he's seen. Lloyd received request what term number 2 from Mykyta and promised to vote for Mykyta. Now Alex receives request what term 2 from Mykyta, but Alex cannot vote for Mykyta. He already promised to vote for term number 2 from another candidate, from Sophie. And Lloyd has the same problem. He promised to vote for another candidate with the same term, and he cannot vote for Sophie.
But cannot we just say that term 2 from Sophie is larger than term 2 from Mykyta, like we did in Paxos?
We can't. In Raft, we use different approach. In Raft, all terms are with the same number equivalent. Now Sophie receives 2 votes, herself and Alex, and Mykyta got away with 2. Neither of them has a majority, so we get a split vote situation here.
So how does Raft deal with that?
By restarting elections. But Raft tries to make sure that those situations are not happening often and resolved quickly. So Raft introduces random election timeouts. Sophie and Mykyta, they don't start immediately. They wait a random amount of time before starting next election. Let's say Mykyta waits for 200 milliseconds, Sophie waits for 150 milliseconds, and then Sophie restarts the election with new term, term number 3. Alex and Lloyd vote for Sophie, and by the time Mykyta wakes up, Sophie is a leader. When Sophie receives response from the majority of the cluster, she becomes the leader, and now she sends all the nodes in the cluster append entries message with her term, her leader ID, and some other information we will cover. Again, remember, Raft has 2 messages, request vote and append entries. Append entries is the second message that in Raft nodes can send each other. Sophie should periodically remind all of us that she is still a leader by sending this append entries message as a heartbeat.
And once the leader is elected, this leader can start servicing the request, because when the client talks to the server to write a command, this client only talks to the leader. And now Sophie can take the request from the iBot and can propagate it to the rest of the members. And this process is called a log replication. Please note that leader election process is over, and now we enter a second Raft subproblem, which is called log replication.
Wait, what is log replication? What logs are you talking about?
Well, in Raft, we maintain a state machine. Every member of the cluster computes the same state by executing the same sequence of commands. And to change the cluster state to a new value, we should all process the same sequence of commands. When we all process change the value to Monday, we have Monday as the state. Change the value to Wednesday, everybody's state is Wednesday. And replicated state machines are typically implemented using replicated logs. And each of us should store a log containing a series of commands, and we execute these commands in order. For simplicity, let's say the command is next meeting is on day X. And please also note that in Raft, the log index starts with 1, not 0. It's weird, I know, it's just the way things are. And commands in the logs can only be in one of two states, applied or committed. Applied means that a member was told this will be a command, but the command is not confirmed yet. It is not final. Final means it's committed. Committed means like it cannot change. It's absolutely final there. And if Alex's logs and Mykyta's logs and everybody else's logs contain the same commands in the same order and they're executed in the same order, they will be in the same state.
So all the members in the clusters, they should maintain logs. What else should they have?
Well, we should all keep track of the last term that we have seen. We should keep the log entries. Each entry contains a command for the state machine and term when this command was received by a leader. For example, a log entry Monday term 1 means the command is Monday, and it was received during leader's term 1. We should also keep an index of the highest log entry known to be applied and the highest log entry known to be committed. So when the iBot tells Sophie we should meet on Monday, Sophie writes Monday to her log, then sends each node in the cluster an append entries message with her term, her leader ID, her log entries, Monday 3 in our case, and her leader commit index, which is 0 now because nothing is committed. So when Lloyd receives this command, he compares Sophie's term to his current term, and his current term is not greater than the term in Sophie command. So he can just append any entries in the command, Monday in this example, to his log, and these entries are not committed yet, they're just applied, and Sophie leader commit is 0. So commit index of Lloyd is not getting updated, and Lloyd just returns true in his response. And when Sophie receives true from the majority of the members, she commits Monday value in her log by updating her commit index to 1, and now she can respond to the client. All good, we're meeting on Monday.
But Sophie also needs to update all the members in the cluster about this new committed state, right? How does she do it?
By sending the same append entries message again. So see, even if we have no new value from the client, she can still use the same message, append entries, to confirm, but this time leader commit will be 1, not 0. So when Lloyd receives this message, he sees that the leader commit is larger than his local commit index, so he updates his local commit index to 1, and so does every other member of the cluster, and the value now becomes committed. See how in Raft we just reuse the same append entries message to notify members about a new value, to confirm the committed value, and also to perform a heartbeat. And in the heartbeat scenario, append entry logs will be empty, but every other field will still be set.
And this model has multiple benefits. First of all, it minimizes the amount of messages. Once again, in Raft, there are only 2 messages, request what and append entries. Request what is used for leader election, and append entries is used for literally everything else. It minimizes the amount of RPC. It also makes it possible to tell the follower about a new value and committed state and perform a heartbeat in the same request. For example, if Sophie learns that new value is Friday, she can send it to Mykyta. And in the same message, she can tell Mykyta, by the way, the last commit index is 1, just in case you didn't know, just in case you missed this update, and new proposed value is Friday, and Sophie is still a current leader. Cool, isn't it?
But what if Sophie sends us all Friday as a proposed message? We all append it, but then Sophie decides she has better things to do and she disconnects. Now cluster has no leader.
Well, one of the nodes, one of us will detect that there is no leader in the cluster and become a candidate again. Who? Well, the follower with the shortest election timeout. Every member of the cluster maintains a timer, a timeout. As we already discussed, this value is randomized to minimize the probability of collision, to minimize the probability of multiple members waking up at the same time. When we receive append entries message, we reset this timer, set it to 0. If we don't receive any append entries message within this timeout, the most impatient of us becomes a candidate. In this example, Alex has the shortest election timeout. He didn't hear from Sophie for 200 or milliseconds. So he assumes Sophie can be out of the cluster. So he becomes a candidate. He increments the current term, votes for himself, of course, and sends everybody request vote message. Mykyta and Lloyd receive request vote message and vote for Alex. Alex doesn't hear back from Vadym because Vadym's satellite internet connection has issues again. But the simple majority, 3 out of 5, including Alex himself, is enough. And when new leader is elected, he tries to finish what the previous leader, Sophie, has started. Alex knows that the last applied value was Friday, but this value has index 2. Alex will not try to commit this value because he also knows that the term of this value is 3. That's why we have term in the log. Alex's term is 4. In Raft, leader can only commit values from their term. So Alex can only commit values with term 4. This is a safety configuration in the protocol. Will we lose the value? No, not really. When Alex receives new value from the client, which is Tuesday, Alex adds this to his log, sends append entries to Lloyd and Mykyta. Lloyd and Mykyta append and confirm. And now Alex can commit this value. Value is Tuesday, term is 4. This is Alex's term. How does Alex commit the value? Exactly, by setting commit index to 3. Right now it's 1. Alex sets it to 3. And see what happens. Now everybody's logs contain Monday, Friday, and Wednesday. And commit index is 3. Friday value from Sophie was not lost. It was committed together with a new value. So if Sophie decides to rejoin the cluster, she will learn that her value was committed. She also will learn all the new values and the new commit index. Instead of Sophie, Vadym came back. He didn't hear back from Sophie, so he decided he can become a candidate. The latest term he has seen was 3, so he increments the term, sends request vote RPC for all the members, but all the members tell him, sorry, Vadym, when you were out, we elected a new leader for this term, so we will not vote for you. And in the next heartbeat message, Alex will tell Vadym that he missed some values. Here's the value he missed, Tuesday, term 4, and the last committed index is 3. So now logs are replicated to Vadym. And this is an example of a failure recovery. Follower, Vadym in this case, failed and then came back. And when he came back, he learned all new values. So in Raft, when followers fail, leader just keeps trying to reach them, sending append entries message. And this append entries message contains everything a failed node needs to know when they decide to come back. And we have already seen how Raft is handling leader failures by electing a new leader. Those two procedures make Raft fault tolerant.
One more question. How do other clients read the value from the cluster? Because we have no learner role in Raft, right?
That's correct. They just ask the leader. If Lloyd's manager wants to micromanage him, and then he really wants to know when we meet next week. So instead of calling Lloyd, he just calls the cluster, and on behalf of the cluster, Alex tells him that the last committed consensus value is Tuesday, and by the way, you should probably consider to stop micromanaging Lloyd.
And what about other properties? We see that Raft can definitely deal with leader and follower failures, but does it guarantee safety?
It does. It guarantees that at most one leader can be elected at a given term. It also guarantees what's called state machine safety. A candidate cannot win election unless its log is up to date.
Does it guarantee liveness?
It does not. Remember split vote situation here? It's still possible. Election can still be happening forever, technically, theoretically. Raft minimizes this probability by introducing this random election timeout. In practice, this live log does not happen, but in theory, just like in Paxos, we cannot rule it out. We cannot prove it impossible. Which one of those algorithms is simpler and which one is more complex, it's up to you to decide. Many people believe draft is simple, but I don't think there is a general consensus on what consensus algorithm is simpler.
But what about real-life usage of Raft? Well, we can just go and take a look at MongoDB. It's a famous Raft-based system. Mongo uses Raft for local replication inside a single shard, inside a single replica set. And remember, then in Raft, all writes should go through a leader. Everybody's calling a leader. So if a slow member is elected as a leader, then the write throughput of the whole cluster is capped by these members' throughput. What if we need to do more writes? Well, since we cannot have two leaders in one replica set, we just need to make sure that each member of a replica set can handle the maximum write load. We need to estimate those write throughput requirements and scale all the nodes accordingly. But what if we hit a limit there because we can only scale up vertically so much? Well, in this case, we can horizontally scale the replica sets themselves. Each replica set will serve a different set of data. We'll split those data into shards, and each shard will have a separate document key range. And we really need to be careful about choosing those keys. We need to choose them wisely, because if keys are not evenly distributed, then some replica sets may end up receiving more traffic than the rest, which is especially painful if your keys are monotonically incremented, because in this case, all traffic may eventually end up on a single shard. You can work around these. You can hash your key. Mongo can even do it transparently for you. Basically, what I'm trying to say here is that in Raft-based systems, you need to be aware of scalability and performance. You need to think about scaling the clusters. You need to think about modeling your data. Basically, you need to make informed trade-offs.
What about other aspects of Mongo configuration?
That's a great question, and that's a loaded question because there is a ton of configuration options. They probably deserve their own talk, but the two most commonly used options are the ones that affect the confirmation of our writes. Remember, in Raft, writes have to be propagated and confirmed used append entries message. And in Mongo, you can specify a number of followers for the writes to be propagated to. By default, in Mongo 5, writes should be propagated to majority, but you can tweak these settings. You can set it as low as 1. In this case, only a leader has to acknowledge it to write it into its logs. But if the leader crashes and never comes back, then your write may be lost. Remember the Raft failure scenarios? The majority option is a way for a cluster to reach consensus, even if some of the members are experiencing issues. Another acknowledgement option to keep an eye on is the disk journaling, because by default, the writes are stored in memory. But if you want more reliability, you may want to force on-disk writes before acknowledging them, so the data is not lost when the instance is rebooted. And that's a trade-off between throughput and reliability again. And that's something that you should decide on again.
Since you know your application and your system is the best, you know its availability requirements and latency tolerance, you know if it's write-heavy or read-heavy, you know which part can deal with eventual consistency and which requires strong consistency, even if it means that you have to deal with the performance penalty. As long as you know what is happening under the hood, as long as you understand how consensus algorithms work, you can make an informed decision to achieve the best outcome and to choose the best solution for your specific problem.
And understanding those algorithms is not just about choosing your persistence layer. This knowledge can and should affect your application design. You should be asking yourself questions like, what is the best way to model my data? Which parts of my application can benefit from distributed consensus and which ones don't really need them? The least you can do is to research what is used in your system already. If your system is using Cassandra or Mongo or CockroachDB as a storage layer, you may go and check which consensus algorithm is used and under what conditions it's used. How does it handle fault tolerance, safety, liveness? What are the trade-offs? Are any of them configurable at all? Your general understanding of consensus algorithm and their trade-offs should help you make your system a little better and your life a little easier.
And when we try to meet for lunch next time, hopefully we can reach a consensus.
We can try.
Thank you for having us here. Unfortunately, we're out of time, so if you have questions, we'll be happy to discuss, to answer them after the talk, because we have 10 minutes to concede the stage to the next speaker. But again, thanks for having us here.